Today, we're going to talk about how the 12-factor app's guidance on configuration applies to common practices in the configuration and deployment of microservices. In this demo, we're going to use the system shown here to illustrate these concepts. The demo uses a sample microservice called Messenger, which is a chat application written in Node.js. It depends on a Postgres database, as well as a RabbitMQ message queue. We'll be running multiple instances of the Messenger service, with NGINX acting as a reverse proxy and load balancer to distribute traffic. We'll also use Consul to keep track of the instances of the Messenger service that are ready to receive that traffic. Before we jump into code, let's take a look at what the 12-factor app has to say about configuration. It defines configuration as everything that's likely to vary between deploys. For example, the hostname and port of your database may be different between staging, production, and your development environment. It also recommends that you provide this configuration to your application using environment variables, which we'll see a concrete example of as we move through the demo. Finally, it recommends that you keep a strict separation of config from code. This makes sense, because if we hardcode something into our application, how can we use the same build of the application to deploy to multiple environments when that configuration needs to vary? Now let's jump into the Messenger application and see some practical examples. This application is a simple Node.js application which uses the Express framework. Here on line 17, we're configuring the Express framework to decode a JSON body. This isn't really the type of configuration that the 12-factor app is talking about, because we're not going to want to change the fact that our application decodes JSON bodies between, say, staging and production. However, if we look at some of the ways that we can configure the JSON parsing, we can have a good example of the 12-factor app guidance. Here, I've provided some configuration that limits the amount of JSON that the middleware will parse to 20 bytes. That is, if it finds more than 20 bytes of JSON in the request body, it'll give up and throw an error. Let's take a look at what that looks like. I'll start our application and then go over to another window and send a simple request using curl. In this request, I'm just going to send the JSON text hello. This is going to fall under our 20-byte limit. Here we got an error, but this is actually a good error. This means that the application parsed the JSON body, looked at it, and decided it wasn't something that it could use. Now, let's send a slightly longer request. Here, the body's just a little bit longer. It says hello, and then I've added comma world here. This will take us over our 20-byte limit. Sending that request, we get a lot of output. However, the key thing to pay attention to here is the error, payload to large error. This is what's going to happen when we go over the amount of JSON that we're allowed to send. So that being said, how can we take it from this form, where we have it hard-coded in our application, to a form that is more in line with the 12-factor guidance? For that, let's take a quick detour and talk about configuration in an application. In a microservices environment, you've got maybe multiple services that your team is owning. You may have people from teams whose services depend on your services coming to look at your code. And often you may be transferring services to other people. Because of that, it's more important than ever to have a very clear central place where things like configuration are defined and explained. In Node.js, I'm using this library called convict, which gives me that ability. It allows me to define in a file named config.mjs a schema for my configuration. So this schema encompasses all of the configuration values that are necessary for the application to run. It also forces us to provide some key information. For example, it makes us include the doc key, which is a human-readable a description of what the value should be, the format, which is how it's going to change the environment variable string content into something that we can use in the application. A good example is if you put true in an environment variable and you put Boolean here, it'll actually convert that to a Boolean for you instead of you having to do it yourself. And most importantly, it tells us exactly which environment variable it's going to look to find that value. So let's add something to the configuration schema to manage our JSON body limit. So here I'm saying, inside the application, we can refer to this configuration value as JSON body limit, as defined here in camel case. I've provided a very detailed human-readable explanation of what it is and what the format is. I've then said, we can find this configuration value under the environment variable JSON body limit. In order to wire this up, there's one more change that we need to make. Let's go back to line 17 here and change it to use the configuration framework. So here we're saying config and .get and giving that name that I defined in the configuration schema here. Now we can fire up the app again and see how we can modify the configuration by changing the environment variable. Restart the application, and here I'm starting it with JSON body limit equals 28 bytes. It's coming up and listing on port 4000 as it was before. Let's clear out all that. And let's send the long request that we did before. This is the one that we just saw error out, but now we're at 28 bytes in our configuration. So that comes through, and I want to remind you, although we see an error here, that means we actually processed the JSON body correctly. Let's go back to the application window here, and I'm going to stop it, and I'm going to bring that value down to 8 bytes. Starting that again, let's go back and run our short JSON body that we saw before, the very first one we ran. Here, we're going to go over our 8-byte limit, and we predictably see that payload too large error come up again. And what this has illustrated is that we can start our application. So the second time that I changed this configuration, I didn't change any application code. I just went here in the command line and changed the value from 28 bytes to 8 bytes. And that gives us the flexibility to, using the same application code, have a very different behavior from our application, allowing that configuration value to vary between various times that we start the application. So now that we understand what the 12-factor app is asking us for, let's take a look at a pattern that is pretty common in microservices environments, but at first glance may appear to violate some of the guidance given by the 12-factor app. This pattern is the pattern of having a folder at the root of your directory to hold your infrastructure and deployment scripts and code. So it sits here as kind of a sibling to your application, and it's often called infrastructure. I've seen it called infra. I've seen it called deploy. It doesn't really matter what it's called. This is just a common pattern that I've seen across various companies. And what this folder holds is a mixture of infrastructure as code, so think Terraform, or if you're using a cloud provider specific offering, something like AWS CloudFormation or Azure Resource Manager. And it also might contain Helm charts. It might contain Kubernetes deploy manifests or config maps, just anything related to the deployment and provisioning of your application, as well as the resources on which it depends. Going back and looking at our diagram here, our team owns the messenger service, and the messenger service depends on this database, and no other service depends on this database. It's exclusively for the use of the messenger service. Therefore, it's common for teams to own both the application itself, which is common from any other pattern, but also to own the provisioning and management of the database on which it depends. This allows us to make decisions about the application as well as the database without having to file a ticket with another team or wait for them to have time to work on our issue. So let's give some examples of what this might look like, and I'm going to create some files and then go through and explain them. But as I create these, I want to note that what I'm going to show you in this demo is not really indicative of what you'll see in this actual pattern in real life. I'm purposefully not using something like Kubernetes or HashiCorp Nomad or Terraform to illustrate these concepts because I don't want us to get too deep into framework specific stuff. Oftentimes when I watch Kubernetes demos, I get lost in all the YAML. And so I want us to go through and use the most simple tooling possible to illustrate these concepts. So in this case, I'm just going to be using Docker and Bash. But as we talk through, I'll kind of let you know what you're supposed to take from it. And the best way to explain it is to enter some code into the messenger deploy script. So I've got a deploy script here. This is going to be what we run to deploy our messenger application. And I've kind of got it divided into two sections. The first section should look familiar. This is your JSON body limit environment variable, and I'm just setting it equal to a value. Secondly, I've got a Docker run command down here. And this is one of the key concepts I want to illustrate with this demo, is that when you're configuring something using Kubernetes or some other framework, it's providing a very systematic way that's well documented to define configuration and where it should be found and how it should all sort of be put together. But at the end of the day, when you deploy something in Kubernetes or any other framework like that, you're running a Docker container at the end of the day. So here I've got a Docker run command, and I'm taking that variable that I defined up here, interpolating it into a string, and using the -e flag to provide it to the Docker container under the same name. So now our Docker container will come up and JSON body limit will be in the environment. And Kubernetes might have some efficiencies or some other patterns of doing this, but conceptually, this is what's going to happen at the very end of that process of deploying a service in Kubernetes. It's going to do a Docker run, and it's going to pass in all the configuration that is resolved via some mechanism. Maybe it might be args, it might be this environment variable flag, but it's going to get passed into the container in that way. Now, looking back at our description of the 12-factor app, it requires a strict separation of config from code. And looking here, I've got a file in my main repository that is defining JSON body limit as 100 kilobytes. Isn't that a violation of what the 12-factor app is asking us to do? And I would argue that it is not, because here, this code isn't getting built into our container. This code is. And so whenever we build a new container image and we'll want to deploy it in staging and production or any other environment, maybe another region, we're going to be using a different deploy file for that. So the deploy file can be changed after the image is built. And for that reason, I think we're still in compliance with the 12-factor application. But why do this? So I think this gives us a few key benefits. The main benefit is that this gets checked in with my application. That means that when I'm reviewing the application code that I wrote here and the config schema here, as we would normally do in code review, the person who's giving me my code review will also be able to look at the changes I've made to the deployment script to provide that configuration to the application. They can then give me feedback about the contents of that deployment script. For example, if I'd left this at 20 bytes, like we had when we were messing around with the hard-coded example, someone might rightly point out, hey, this is way too small. If we release this to production, almost all of our JSON body decoding is going to start failing and we're going to have an incident in production. You should raise that to a more reasonable value, which I might respond, oh, I'm sorry, I totally forgot. I was showing someone how it fails and I forgot to change this. So these type of errors can be avoided. And having everything go through your process, everything that you're responsible for, as well as sort of spreading that responsibility out to the team is a great practice for microservices, because a lot of this is more about responsibility and management now of both your application and the infrastructure that you own along with it. With that long explanation out of the way, let's take a look at the two types of configuration that we're going to deal with in this example. And these aren't formal types of configuration. These are just something that I've come up with as a way to think about it. But it's relevant to the case of the deployment script because we're going to be handling them differently. So the first type is specified directly in the deploy script, and we just talked about this. So these are things that we know right now. We're going to hard code them in. I know that I want to have 100 kilobytes of JSON body that I'm willing to decode, maybe in production and in staging. And these are things that we can talk about in code review. So I'm going to take these and enter them in. I've added a few other ones, like which port the application is going to listen on. I add them here up top, and then I'm going to add them down here as well to be injected into the application when it starts. So same pattern. I'm saying node env. I'm taking the value of node env that I've defined up here and supplying it to the application via an environment variable and the -e flag for Docker run. The next type of configuration is going to be the type of configuration that is pulled from the surrounding environment at deploy time. This is stuff that we can't know when we're sitting down here in our text editor writing the configuration. And this is stuff like the location of our database. So we might maintain the provisioning scripts. So for example, Terraform. In our case, it's just going to be a deploy script. We might maintain the way that this is stood up and we own it. But if we're dealing with a cloud provider, for example, it may provision it and give it some host name that we don't know at this point. So it's better for our application to come up, and as it comes up, say, hey, I need a database. Here's what I know the key is called. Where is it? And have the system provide an answer from some source that is available in multiple locations. The same thing is going to be true for the RabbitMQ message queue. This is probably not going to be owned by our team. Usually infrastructure like this, in my experience, is owned by another team. Sometimes they're called the infrastructure team or the platform team, and they're responsible for making sure that the message queue is up and running at all times. They're going to also register this resource with the system under some name, and we're just going to come up and say, hey, I need a message queue. Where can I find that? So going back to the deployment script, let's see an example of that. So we talked about the database host name. What I'm going to do is I'm going to take the return value of a curl I send to the Consul key value store. And I'm just using the Consul key value store as an example. Probably in production you might be using something else. But what the Consul key value store gives us is a highly available resource that I can ask for a key and get the value. And that's what I'm doing here. I'm sending an HTTP request using curl to the Consul key value store. And I'm asking for the messenger-db-host key. I'm going to assign the value that I get back to the PG host variable. And then just as we were doing before, I'm going to inject it into the container using the -e key, -e flag that we can use with Docker run. Now I'm going to add the rest of the Postgres configuration here, following exactly the same pattern. It's going to look a little bit long, but we will add it anyway. And one thing I want to note here as I add this last piece is that I'm going to be putting the password in here, pulling it from this console key value store and putting it down into the Docker container. This is not something that you should ever do. This is not an example of how you should handle passwords. You should always be using a dedicated secrets management tool. And the method by which you inject that password that you have in your management tool into the application may not be something as simple as an environment variable. You may be using more secure methods to get that into your running application. But because this demo is all about configuration and not about secrets management, I've decided to gloss over that for now. But I just want to underline again that this is not something that you would ever do. So that gets us our configuration as defined in the configuration schema over here. So you can see PG database, PG port. That gets us our Postgres database configuration. The next thing that we got to add is our RabbitMQ configuration. And this, as I said before, falls into the same second category, which is configuration that's pulled from some outside source at deploy time. So we're going to ask for AMQP host and AMQP port when the application comes up. And we're going to assume that those are provided by the team that manages that application. That resource. So I'll add those to be injected in the container. And here now we have a fully runnable instance of the messenger deployment script. So these have all of the values that are here in this config schema that we defined earlier. So in order to get running, we'll need to define a similar file for the database. And I'm going to go over this one a little bit more quickly. But in reality, this might be something like a Terraform script. Here we're going to just use the same pattern that we did before, where we're defining variables like port. And this is something that we then inject into the application for the, not the application, the container for the startup and configuration of the database on which Messenger depends. Next, we're going to see how we register that information with the aforementioned console key value store so that it's available for instances of Messenger as they come up. So here I've got some pretty simple requests, and I'll take a look at the port one as an example. So here we've defined port and we're passing it into the database container like this. And then we're going to take that same value, port here, and send a put request to the console key value store to create or update that key in the console key value store. So Messenger DB port is going to be set after the database comes up and we know it's listening on that port. And then we're going to pull it here with the same key and assign that to PG port and inject it into the container here. And this is how the Messenger application is going to ask for and get the configuration that it requires when it starts up. So the last thing we got to do is go back to the command line and send a few more commands to mimic the registration of the RabbitMQ broker as we've done with our database. And this is in our demo world managed by another team. So we're just going to assume that they've done that. We're not going to write a whole deploy script for it. So the next thing we'll do is we'll build our application as a Docker container. And this is going to be, in real life, this would be some CI process that would spit out a container image, but here we're just building it manually. And then I'm going to go back and simply run the deploy script for our database. So that takes care of starting up the database. That's the container ID, and then it's going to register all of those values with the console key value store. And then we can take a quick look at the console key value store before moving on. The UI for the console is over here at localhost 8500, and if we go to key value, we can see that now we've got the database DB host, we've got the DB port that we talked about earlier, and those values are all saved in the key value store for the Messenger application to come up and ask for. So now let's deploy our Messenger application using the deploy script that we wrote. Okay, that's a lot of output, but this is all of the requests that are going in to get the values of the configuration for the Postgres database and the RabbitMQ queue. So now if we look at Docker, we can see that we've got an instance of our Messenger container running and our Postgres container running. So our two deploy scripts worked, and everything is running as we expect. And we can further confirm that by looking at the logs of the Messenger service and seeing that it's up and running and listening where we expect it to listen. So I'm actually going to shut down that service for a moment. And then I'm going to talk a little bit about service discovery, because that's our next step. Now that we've got the container up and running, we need to provide a way to expose it to the outside system as a whole so that people who want to query it, or maybe other services that depend on the Messenger service, can get access to the Messenger service without having to worry about querying specific instances of the Messenger service. And this is where NGINX comes in. We're going to use NGINX as a reverse proxy and load balancer to take in requests that are meant for the Messenger service and distribute them correctly. Now, before we talk about how we're going to handle this, we need to understand how NGINX handles configuration and dynamic services that are coming up and down. Here's an example NGINX configuration. It is using a directive called upstream to define explicitly the servers that it's going to route to. The upstream is given a name. In this case, I've called it Messenger service. That Messenger service upstream is passed to the proxy pass directive right here. So it's saying if we hit this location, then proxy to any of these servers defined in the Messenger service up here. However, you'll note that the servers here are explicitly defined. I load this configuration and NGINX knows that these two servers are there and it's going to route to it. Let's take a look at this visually and see how this works when we have multiple instances of the service going up and down at the same time. So here's an example of some requests coming into NGINX. NGINX is then going to route it to one of the Messenger services. This is fine. This is what we have in the example. However, if we start up another Messenger service next to the existing one, NGINX doesn't currently know it's there because NGINX is referencing this block here, which only has Messenger 1 at this point. So how do we solve this problem? Well, we make our Messenger service register itself with the Consul service registry when it comes up. We then have a little agent that's running next to NGINX in its container that's looking at the Consul registry and reacting to changes. This is a tool called Consul template that's provided by HashiCorp. When the Messenger 2 instance comes up and registers it with Consul, Consul template will react to that and re-render this configuration based on a template and provide that configuration with a new set of healthy servers to NGINX. It'll then trigger NGINX to reload itself and reconsume that configuration. And NGINX can do so without incurring downtime, so this is a pretty smooth operation. That's how we're going to manage it, and so let's set it up. For this, I'm going to go back into the application code and add some references to a Consul registration module that I've written prior to this demo. This code will be available on GitHub, and I'm not going to go over it in detail because it's pretty basic, but it just uses the Node.js library for Consul to do a simple registration and define a health check. All we need to do is import that module and invoke the function after the app has started listening. This is going to make our application come up and register itself with Consul on start. The last thing that we need to do is go back to the config schema and add a little bit more configuration to handle the provision of the Consul service name, the Consul host, and the Consul port, because the application is going to need to know where a Consul is when it comes up. And again, we don't know that for sure. Now, we can go to our deploy script and add those configuration values. So this is, again, going to be a change that I could submit, into code review, and you'd be able to look holistically at the various types of configuration. So here's the good example of that type 1 hard-coded configuration. I want my service name to be the same wherever I come up. And then I'm also going to provide some information that pulls information from the system. This is that type 2 configuration. And just a reminder, this is my way of thinking about it. Type 1 configuration and type 2 configuration aren't formal terms that everyone knows. But here, I'm kind of depending on the fact that the team that is managing Consul has provided me Consul host and Consul port in the environment. This is pretty common, and I've seen it at a few places I've worked, where this is kind of the most basic piece of information any service needs to know to get up and running. So the team that's managing the provisioning of hosts upon which the service is run always makes sure that this information is available at least on every service so that they can come up and start asking for service registry information. And finally, I'm going to provide these values that I've just defined into the Docker run command using the same strategy I've been using throughout the whole demo, passing it in as an environment variable using the -e flag. And now we're ready to go. So I'm going to have to rebuild my Docker container for Messenger since we've changed the code. So this would be an example. I've now got my code review to, approved. I'm going to now put it through the CI process, build a Docker image, and then we can deploy it. So now I'm going to start deploying them. So this is my command to deploy it, and I'm kind of mimicking that console host and console port being in the environment. So I'll run this. I was in the wrong directory here. I'll run this, and we can see it starts up just as it does before. We can make sure that it started up by doing this again. We can see it's up and running. And I'm actually just going to run this a few more times because we're mimicking a situation where we've got multiple instances of the Messenger application up and running. And to confirm this, we're going to go take a look at the console UI again. And this time we're going to go to the Services tab, and we'll see that we've got some unhealthy Messenger services. And this is because they haven't quite passed that threshold of having the health check return with the frequency that's needed. But I see that they've now all gone green. So we have a nice stable of 3 Messenger instances. Next, I'm going to really briefly go over this. This is something that, again, you can find in the code. I'm going to provide a deploy script for the load balancer, the NGINX load balancer. And then I'm going to put the configuration for that into the deploy script. This code is available on GitHub. And just real quick, an example of what's in there. There's a Docker file which installs that console template and gets everything set up. The template that we provide to console template looks like this. You might recognize the upstream here. And then you've got some Go templating here that's looking in console for the messenger service, and then sort of doing a loop and adding all of those as a server block into the upstream, and otherwise it looks the same. We provide configuration to the console template tool like this, and we give it that template that we just showed you. Here's the source, and we want you to template it and send it out to this location in the container, which is where NGINX is going to look for its configuration. And then we're going to say NGINX reload or start NGINX if it's the first time. So that's a basic overview of what's going on there. We'll create this deployment file for the load balancer and reverse proxy that has the console host and console port specified. Again, providing it to the Docker container using the -e flag. So with all that up and running, I can start that up. I'm going to ask the load balancer to run on port 8085, and that's up and running. So now we should have everything up and running, and we can finally make a request to our application. So we're going to do curl local host, and we're going to do 8085 because that's where our NGINX reverse proxy is, and I get back an OK. That means we are actually going through and hitting one of those instances. I can get a little bit more information about that request by passing the -i flag, and I want you to take a look at the upstream IP value that's coming back. That's going to be the IP address that the request is ultimately being served by in the messenger application. So if I run this command a few more times, you can see that that IP address starts changing. We've got 0.6, 0.7, 0.8, 0.6, 0.7, 0.8. That's the round robin load balancing strategy at play here. So we know now that NGINX is up and running and distributing requests from downstream to these upstreams here, and doing so in order. So that's the system all set up. Go back and look at how we were working before. We've defined configuration in the messenger application using an explicit schema. We've then defined a infrastructure folder at the base of our application that lives alongside the rest of the code, and it gets checked in and goes through code review with the rest of our code. And that is information related to the configuration and deployment of our service, as well as its dependent resources such as the database. Speaking of the database, I'm going to do a quick setup of the database so that we can use the messenger service via the command line and finish off our explanation. And as these are running, I'll talk a little bit more about what we learned. So as I said, we've got the configuration well defined in the service. We've got the deploy scripts that are sitting there next to our application, pulling information from the system on deploy, as well as using predefined configuration that we supply at the time that we write the change to the application. And it's allowing our team to put everything through our processes and be confident about what we deploy. Okay. Okay, this is going to be the last thing that we're going to do here. And then we'll take you through some basic commands. All right. So now I'm just going to create a conversation, and this is going to be a fully command line based conversation here. So we have a conversation coming back from our service. I'm going to then send a message. It's going to be a very interesting message. It says this is the first message, and it's from James. I'm going to then reply to James from the other participant named Norm Lavian, and they're going to say this is the second message. And then finally, we can query the whole set of messages for the conversation and see them here. And again, all of these requests are being distributed between the various instances of the Messenger application. Thanks for sticking with me through this demo. We'll notice that this is a lot of setup to get a simple service set up. However, it's really aimed at making that inter-service communication good, at making the system be very predictable, and optimizing our flows to incorporate the human factor and have communication within the team and explicitly allowing other teams to come in and understand what we're doing when we're maintaining services, and we have to care how we look outward as well as how it functions inside our team. Thanks.